Okay, hopefully your derivative video was helpful in reducing the intimidation of calculus and not increasing the intimidation of calculus. I do want to remind you that the use of calculus in this class is going to be limited because our chief objective is for you to learn physics, and the secondary objective is for you to familiarize yourself with how calculus can be used as a powerful tool. So that being said, I'd like to approach integrals. I know that integrals can get really gritty once you get into especially calculus 2 and the techniques of integration. So what I'd like for you to understand about our use of them in physics is that even in upper level courses, it is not our intention to force you to go back through the process of using integration by parts or one of those really, nasty methodologies. It's useful to know how to do that stuff, but your chief objective here is to solve problems. So we'll frequently use integral tables to solve the more complicated integrals. Your objective in here is to understand what an integral means and what it's actually accomplishing. So let's take a look at some simple applications of integrals so that we can kind of get our minds around the purpose and the method. So the first thing that I'm going to do is talk again the same way that I did about, previously about derivatives. When we have the first thing that I wanted to bring up is the polynomial method. So this is the operation of taking the integral of a polynomial function f. And of course, you've seen this. Oh my gosh, I remember that thing again. Or maybe you haven't seen much of it, but you've seen a little bit of it. And I don't want you to be terrified of this thing. What I want you to do is look at that and go, okay, that's just a method. Let's get our let's get our minds around why we're doing it. So the whole point of an integral is really just to if I have um, fluctuations in, let's say, the way that I earn money. I would like to be able to ignore the fluctuations um, and allow the mathematics to pay attention to those fluctuations for me so that I don't have to consider them bit by bit and just basically get to the bottom line. How much money did I make? So the whole point of an integral is to be able to rapidly add up features of something without having to get into the details of how something is changing. Our example that we'll be using in this video is density. So if an object is changing its density, we would like to be able to find out what the total mass of the object is without having to worry about whether that density is changing at one location or another. We'd like the math to take care of that for us. And so as long as we're able to track that change in density mathematically, then the integral will take care of it for us. And that's beautiful. And that's something that I think that students would be a little happier about if we were able to introduce this in a way that is a little less intimidating. So let's go ahead and, oops. Let's go ahead and start with an example of, as I was talking about, a bar. So I've got a bar here, and it's going to have a constant density to it this time. So if I have a constant density to my bar, then when I take an integral, essentially all I'm doing is just breaking it up into bits and counting the bits. So I will begin by saying that this is going to be 70 bits, let's say. I think this is about 70 bits. So we have 70 bits. And I'll call them, I'm breaking it up into n equals 70 pieces, right? Essentially what I'm doing here is I want to know what the total mass of this is. Each one of these little bits is going to be a mass dm, okay? And that little mass dm is, let's say, 1 gram. Okay, if this is a constant density object, then it's really easy for you to look at this and know immediately what the mass of this object is, right? If there's each bit is 1 gram and there's 70 bits, then you add them up. That's the essential idea behind calculus. So we would, in this case, take the integral of all of the little dm's, and that's going to give us, in other words, we're summing up all the dm's from 0 to our 70th dm, and that's going to give us the total mass, right? Okay, So this would be okay. So if we were to now, I want to get rid of that because this. Let's see. I'm going to go ahead and also get rid of this limit of integration because the limits change according to what you're actually putting in your integral, right? This is still going to be true regardless of whether we change our density or not. But now what I can do is I can change the density to a new function. And that function, let's call it the density. I'm going to use lambda as my density because this is common in physics. We call this a linear density. In other words, it changes density from left to right, but not from up to down or back to forth, any of that. We're just doing one dimension. So it's going to have some density function. I think I'm going to go ahead and just write this as 12 minus, that would be 12 grams per centimeter. And I'm going to give it a length of 140 centimeters. So we're going to have 12 grams per centimeter minus 0.1 gram per centimeter squared times the distance in centimeters. Okay. What that means is that when we have x is equal to 0 right here, we could we would have a density of 12 grams per centimeter for this first piece. And then once we get to the end here, it's going to have an entirely different density, right? Okay, so let's go ahead and figure out how we're going to how we can get the mass of this whole thing. Because when you're counting this up a little bit at a time, there's actually going to be a little bit of error if we were to say, oh, let's cut this into 70 pieces. We cut them into 70 pieces. Each one of these is going to be 2 centimeters long, and I'm going to have the wrong density here. I'm going to call the whole thing 12 grams per centimeter for that first 2 centimeters. That's not true. It actually is decreasing a little bit, right? So this integral actually allows us to find the mass of the entire thing. Here's the thing that I want you to get a sense of. That a lot of the times students don't know what to put in the integral. But the thing is, the integral itself tells you what to put in there. So all you have to do is follow the method. Here we have, if I want the mass of this thing, I just need to take the integral of all the individual masses. Now, clearly there's more to this. I have a distance and I have a density. So my objective next is to say, what is this thing? How do I turn this into something that makes this doable? I would like to add up all of my individual masses with different densities in them. So I clearly need something in density, linear density here, that is related to mass. Well, the linear density is given as what the mass is over the length. That is the definition of the linear density function, right? We would like to know if I have certain dm, how does that change? How does this change with x? So if I move over to some new x, let's say this one here, I think is somewhere around 20 blocks, and that'd be about 40 centimeters. Then what is my new mass for that individual piece? Now, we would, in fact, break this up into many more than 70 pieces. It would be infinitely many small pieces, so that an infinitely small dm at an infinitely small distance change would still be accurate, and it would be accurate within this function. So don't worry so much about what I mean by that. The whole point here is for us to look at this and say, I know that this is the function that compares linear density to distance. Well, that's important for me. Why is that important for me? Because all I'm going to do is just replace this dm. How do I do that? Well, there's a dm. All I have to do is rearrange this equation. If this is true, then that means that this is also true, isn't it? So now I have something I can get a hold of, and that's the important part of figuring out how to use an integral. I've got dm is going to be now replaced by lambda dx. Wonderful. I got something I can do now. That's the whole point of calculus. We got to take this very simple idea that if I add up all the individual masses, I get the total mass. That's the general idea behind integrals in calculus. And then all I got to do is just change dm to something useful, right? That's the whole idea. Now, because I'm I'm integrating over x, then my integrals can have limits from x equals 0 all the way to x equals 140 centimeters. So now all it takes is just plugging stuff in. See, this is the hard part, really. Figuring out what this is the hard part. The rest of it's just what you've learned in calculus already. So now all I have to do is just put my 12. I'm going to leave out my units here because it looks messy if I don't. 12 minus 0.1x. And then, of course, that's lambda, so I've still got my dx. I got to sum up over my dx. And then that is going to become two different integrals. It's a little easier to grab a hold of that way. Okay. This just integrates to x, so it would just be 12 times x from 0 to 140, excuse me. And this one is going to go 0.1, and that integrates to, this x integrates to 1/2 x squared. And again, I'm going from 0 to 140. And so here, the 0 end is not going to contribute. We're just going to have 140 here and 140 here. So I'll get 12 times 140 centimeters minus, or grams per centimeter times 140 centimeters gives me this should give it to me in grams. I didn't include my units, but they will work out in grams and centimeters. This would be 1/2 times 0.1, and then 140 squared. Again, this will work out in grams. Okay, I plug that in, and I get 700 grams. Quite a bit heavier than the last one, but I guess we started off with a very dense end here, so that's okay. All right, so this is the general idea behind integrals. We can also, you will sometimes see integrals in 2 dimensions, and it's totally fine to turn this into, instead of this being a amount of mass per unit length, using an amount of mass per unit area. We could do that if we had, let's say, a disk or a plate or something like that. The density per unit area. That is going to require a double integral. I don't want to get into that in this video, but essentially, I'll just give you the rundown of what we would be doing differently. If I don't want to get into the actual calculation, but if you had a plate that was something like this, then we would have to do an integral over both dimensions. And if we had a density that changed like this, let's say, very dense in the corner and then not so dense out here. If that were the case, then we would need to go through the same process where we start off just finding what is the mass of this plate. I just need to add up all the individual dm's. But in this case, dm is a little bit more complicated because it's given as little area masses. In this case, the dm was just one length, right? So we just cut a chunk. In the case of the plate, we're going to have something a little different because we're going to have this dm and this dm and this dm and this dm. So we actually have to add up all of them over both dimensions, x and y. So mathematically, that's not so bad. All we're doing is just using this instead of this. We replace dm then with the area density instead of the linear density times each individual dA that's associated with a dm. Every time we have a little dm, there's going to be a little dA associated with that. Now that little dA, if you zoom in, is simply dx times dy. So that allows us to change this area integral to an integral over x and y. And all we're doing is just replacing dA with dx dy. Okay, so we're not going to go into how this is done. Hopefully you'll have some experience with this as we're moving on. And occasionally we might run into something like this in physics. Again, this is not going to be something you're going to be tested over. This is just an extra tool that I want to familiarize you with in this class so that when you get to upper level classes, it's not going to be so tricky. When you get to electrodynamics, when you get to fluids, when you get to heat transfer, a lot of these are going to require triple integrals. So it's best to go ahead and try to get a little bit of a grasp of this stuff right now while it's easy. Okay, so again, please don't freak out about calculus. We're just going to try to give you a heads up on calculus this semester. You will be demanded out of you in future classes, but will not be heavily demanded out of you in this class. Certainly nothing on a double integral level. So, okay, if you've got any questions, I'm here for you.